quicker than the texture of space-time, can stay aware of it and it'll simply tear, and I'm panicked by this presently. Our night sky is changing quickly, and in simply a question of many years, if not less, it could turn out to be totally unrecognizable. Cosmologists overall are sounding the alert. Specialists like Neil deGrasse Tyson have as of late affirmed the inescapable blast of Polaris, and the story behind it is very startling. Polaris, known as the North Star, has for a long time been a constant in our night sky, filling in as a crucial reference point for stargazers, guides, and cosmologists. However, this could soon change, adjusting our night sky and furthermore cosmic estimations. Let's dig into the meaning of this threat and its implications for us all. For quite a long time, Polaris has guided sailors and stargazers alike, standing firm on a worried footing as a guiding light. Its unfaltering presence in the night sky has been fundamental for navigation. However, this stability may soon be upset. In September 2023, a research paper presented by the respected Royal Astronomical Society cast doubt on the destiny of this divine illuminator. Polaris is near the very edge of detonating, potentially disappearing from the night sky forever. Before we investigate the results of this disclosure, let's see more about Polaris. Also known as the North Star or P-star, Polaris is unique because of its nearness to the celestial North Pole. Positioned nearly straight above Earth's North Pole, it appears almost fixed in the northern sky. Found in the constellation Ursa Minor or the Little Dipper, Polaris shines as a moderately radiant yellow-white supergiant star, a lot larger and brighter than our Sun. It's not a singular star but part of a complex triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris B orbits around them. The interactions between these stars create gravitational forces that shape their orbits and influence their behavior. Any disturbances in these connections can lead to unpredictable variations in the star's brightness or pulsation patterns. However, the specific mechanisms behind these interactions remain unclear. Polaris is located about 323 light-years from Earth, meaning the light we see from it today began its journey over 300 years ago. Consequently, if Polaris were to detonate now, we wouldn't notice it until over 3 centuries later. The fact that Polaris has made it this far makes it even conceivable that it has already detonated and we are yet to witness the light from that event. Since ancient times, the North Star has held enormous cultural, navigational, and symbolic significance. Its stability and fixed position made it a valuable guide for ancient pilots, helping them navigate across oceans and lands. Symbolically, Polaris represented steadiness and direction, remaining steadfast amidst the ever-changing night sky. For astronomers, Polaris served as a crucial reference point, assisting in the study of celestial movements and variable stars. As a Cepheid variable star, its periodic variations in brightness have provided valuable insights into stellar properties and the nature of variable stars. This characteristic also played a crucial role in determining astronomical distances and aligning instruments. These pulsations follow a predictable pattern, which has been the standard for the star, making it easy for us to anticipate its behavior. However, recently Polaris has deviated from this normal behavior. This anomaly in its pulsation cycle has puzzled astronomers, leading to closer examination of this celestial anomaly. Rather than its typical predictable pattern, Polaris has begun to show inconsistent periods of dimming and brightening. Researchers are now raising concerns that the star might be approaching the end of its life. This lines up with behaviors commonly seen in stars nearing the end of their life cycle. The gradual lengthening of Polaris' pulsation period, which was once stable, can be attributed to interactions within its stellar system. We've noticed an annual increase in the pulsation period of 4 to 5 seconds, which might seem insignificant but holds serious implications. Some space experts suggest that gravitational interactions between the Polaris stars could be causing these changes in its environment, directly influencing its pulsation patterns. However, others are more alarmed, believing that the star is near the brink of detonating. The similarities between Polaris behavior and that of Betelgeuse, another prominent star in the Orion constellation, are striking. Both stars have shown astounding anomalies in their luminosity, raising concerns about potential explosions. Red giant stars in their twilight phase often show such inconsistencies before reaching the peak of their life cycles. While NASA has expressed heightened concern about Betelgeuse, similar attention has not yet been officially directed toward Polaris. As a red supergiant star approaches the end of its life cycle, it passes through various stages, including the main sequence, red giant stage, and finally the supernova explosion. Based on Polaris' unpredictable pulsations, researchers predict that it has entered the helium-burning phases typical of stars nearing their end. These anomalies in Polaris behavior align with patterns indicative of supergiant stars in their twilight stages. However, definitive signs of its impending supernova remain uncertain. Astronomers are steadily analyzing these anomalies to understand Polaris' destiny. If Polaris were to go supernova, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for a long time, weeks or even months. Its appearance could dramatically alter the night sky, briefly modifying our perception of familiar constellations like the Big Dipper or Ursa Minor, of which Polaris is a part. Rest assured, Earth would almost certainly be completely safe, even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually astounding as Betelgeuse's, it could still be visible to the naked eye for an extended period and eclipse nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers worldwide. However, the specific visibility and impact on Earth's environment or atmospheric conditions would be less significant compared to a closer supernova event. But what about Polaris itself? What will its fate be after a potential supernova event? Let's clarify one thing. While giant stars typically end their lives in a supernova explosion, this is unlikely to be the case with Polaris. When a massive star goes supernova, a tremendous explosion occurs within it, marking the final catastrophic stage in its life. This cycle involves a complete collapse of the core, triggering an immense shockwave that causes the star to explode violently. However, Polaris isn't large enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This change will not result in a supernova explosion, but rather a quiet end as it evolves into a small, incredibly dense celestial remnant. A white dwarf is the remnant of a low or medium-mass star that has exhausted its nuclear fuel. It is incredibly dense, about as massive as the Sun but compressed to the size of Earth. When this happens, we will no longer be able to see its remnants from our planet in the same way we observe the star today. Comparing the expected impacts of Polaris explosion with historical supernova events provides valuable insights into the evolution of stars and their ultimate fates. Comparing our expectations with actual observations such as SN 1987A and later events like SN 2011 Fe or SN 2014 J provides significant information for understanding the potential consequences of Polaris demise. SN 1354, for example, resulted in the formation of the Crab Nebula, a nebula that continues to grow and emit radiation across different wavelengths, offering astronomers a rich field for study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, gave insights into the processes of nucleosynthesis and the properties of supernova remnants. For instance, the development of nebulae, the release of cosmic rays, and variations in brightness can offer insights into Polaris' unique characteristics. The formation of clouds like the Crab Nebula results from the expulsion of material during the supernova explosion, which interacts with surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the process of stellar birth and death. Additionally, the release of astronomical rays, high-energy particles accelerated by the supernova shockwave, has implications for astrophysical processes and cosmic radiation conditions. To make an authoritative comparison, researchers assess the differences in mass, composition, and speed of expelled materials between Polaris expected burst and other observed events. This involves analyzing the light curves, spectra, and remnants from these events and projecting similar attributes for Polaris expected burst. Evaluating whether Polaris explosion could lead to the formation of nebulae or particular elemental distributions enhances our understanding of its likely outcomes. Another essential area of investigation involves assessing the pulsational variation of stars approaching their end stages, such as Polaris, compared to observed supernova progenitors. This close examination can help verify similarities or deviations, providing insights into the explosion mechanism. Pulsational variation in stars nearing the end of their lives may indicate internal instabilities or impending catastrophic events, offering clues to the evolutionary processes leading up to supernova explosions. Despite careful observations and extensive analysis, astronomers remain puzzled by the anomalies observed in Polaris behavior. Unraveling the complex conditions driving these inconsistencies holds the key to advancing our understanding of stellar evolution. Understanding the forces behind Polaris' unpredictable pulsations requires interdisciplinary collaboration and the development of advanced theoretical models and observational techniques. The potential loss of Polaris as an essential reference point in the night sky presents significant concern for astronomical endeavors. Ground-based telescopes and celestial measurements would require recalibration, affecting the accuracy of galactic estimations. The absence of Polaris could also impact navigation systems and cultural practices based on celestial landmarks, highlighting the importance of this celestial event. The complex behavior displayed by Polaris underscores the need for deeper investigations and dedicated research efforts. Astronomers must grapple with the intricacies surrounding its unpredictable pulsations and present, tangible answers. Recognizing the importance of advancing our understanding, we might eventually unravel cosmic complexities. At last, the answer to Polaris' fate remains uncertain, and only time will reveal its true essence. Regardless, the quest for knowledge and understanding in the face of infinite uncertainty is a testament to humanity's enduring curiosity in unraveling the mysteries of the universe. As we contemplate the fate of Polaris, it's essential to recognize its role not only as a celestial marker, but as a window into broader cosmic phenomena. The North Star has been crucial in expanding our understanding of the night sky. Ancient cultures used its position to develop calendars and seasonal agricultural practices, linking celestial events to natural activities. As civilizations advanced, Polaris' stable position provided navigational aids that facilitated exploration and trade, marking it as a foundation of sea history. In modern astronomy, Polaris serves as a vital alignment point for telescopes and observational instruments. Its reliable brightness has allowed astronomers to refine their measurements of distance across the universe. The star's predictable light output contributes to the cosmic distance ladder, a fundamental tool for measuring distances to distant galaxies and understanding the expanding universe. Interestingly, the study of Polaris also opens avenues for investigating stellar evolution. By analyzing its life cycle, researchers gain insights into the broader life cycle of similar stars. The properties of Cepheid variables, including their pulsation periods and luminosity variations, allow scientists to draw comparisons with other stars, enhancing our understanding of stellar characteristics across different stages of life. As we investigate the final stages of a star like Polaris, we must also consider the implications of its potential transformation into a white dwarf. This process is a fate shared by many stars in the universe, leading to the formation of stellar remnants that will persist for billions of years. The study of white dwarfs has significant implications for our understanding of stellar and cosmic evolution. Additionally, the relationship between dying stars and their environments is a fascinating area of study. When stars shed their outer layers, they contribute to the interstellar medium, enriching it with heavier elements formed through nucleosynthesis during their lifetimes. This recycling process is essential for the formation of new stars, planets, and ultimately life itself. By examining the remnants of stars like Polaris, scientists can trace the pathways of matter throughout the universe. The potential explosion of a star like Polaris raises questions about its impact on the surrounding cosmic environment. While its distance from Earth provides a layer of safety, the energetic phenomena associated with supernova events, such as shockwaves and the release of high-energy particles, can influence nearby star formation processes. This could lead to bursts of intense star development or trigger the collapse of gas clouds, resulting in the birth of new stellar systems. Despite its scientific implications, the story of Polaris also raises philosophical considerations about humanity's place in the universe. As our understanding of cosmic life cycles grows, we are reminded of the transient nature of celestial bodies. Just as Polaris has guided humanity for centuries, its inevitable transformation will mark a change in our night sky, serving as a poignant reminder of the inevitable changes that permeate the universe. Astronomy has often inspired questions about the fate of our planet and species. As Polaris approaches its potential end, it encourages us to reflect on our own existence and the legacy we leave behind. The pursuit of knowledge about stars like Polaris fosters a sense of wonder and curiosity that transcends generations. Finally, advancing observations and breakthroughs in technology will allow astronomers to monitor Polaris more closely than ever before. Upcoming telescopes and space missions are designed to capture remarkable detail in celestial behavior. These observations will not only shed light on the life and death of Polaris, but also enhance our understanding of the broader universe. In conclusion, the story of Polaris extends far beyond its immediate visibility in our night sky. It encapsulates centuries of human exploration, serves as a vital benchmark for astronomical measurements, and invites us to contemplate the deeper questions of existence. As we watch the fate of this beloved star unfold, we participate in a larger narrative about the universe, a story that continually shapes our understanding of life, time, and the cosmos itself.